So in this video, we're going to look at doing some hypothesis testing examples, and we're looking at large sample size. So the first question states, a researcher reports that the average salary of first-year graduates in IT is more than $42,000. A sample of 30 IT graduates has a mean of $43,260, and at alpha equal to 0.05, test the claim that IT grads will earn more than $42,000 a year. The standard deviation of the sample was found to be $5,230. Now with this question, there is a bit of detail that we have to unfold here. First of all, this alpha is the area of the tail or tails, depending on if it's a first or if it's a single or a two-tail situation. So just understand that this is the probability of making a type 1 error. That's what we had determined alpha to be. Now, looking at this question, first thing we want to do is to determine, is it a one-tail or a two-tail situation? Well, let's state the hypotheses, because that's the first step. Now, it says here that graduates in IT is more than $42,000. So that's the claim, right? The average salary of first-year graduates in IT is more than $42,000. So that means we should use this information to state our hypotheses. Pause the video and see what you come up with. So if it says more than, then we know that the mean has to be more than $42,000. And that means that the null hypothesis is less than or equal to $42,000. So that's step one. State the hypotheses. Step two is to find the critical values. Well, by critical values, we're going to take the hypotheses, and you can see that this is a right tail. And what we're going to do is we're going to draw the picture. And since it's a right tail, we're going to draw it like this. Here's our tail, and this is where this comes into play. That means that the area here is 0.05, or there's a 5% chance of making a type 1 error, rejecting each knot when it's in fact true. Now the question is, what is the Z value going to be when this area here is 0.05? Well, we have the means to make that happen. Well, we know that from the mean to this point must be 0.4500. And when we look at our Z table, we're going to go look for the area of 0.4500. And what does that give us? So in this case here, 0.4500 is right smack in the middle here. Now, what's preferable is that you actually go with the larger of the two values. It increases, it makes the standard better. So this gives us a value of 1.65. So our critical value is 1.65. So what does that mean? It means that the Z value here is 1.65. And so that's the fence. 1.65 for Z is the fence. If you're on this side of the fence, you do not reject H naught. If you're on this side of the fence, you do reject H naught. Now, what does this mean for the next step? Well, the next step is to actually perform the Z test. All right, so we're just going to take our sample mean from the population mean and divide it by standard deviation divided by square root of sample size. I'm sure you can do this math. Let's take our information and plug it into this formula and see what we get. Take a minute to pause the video and give it a shot. So if you got the following, then we're on the same path. The sample mean was measured to be 43,260. The population mean, or the claim that we have, was 42,000. The standard deviation was $5,230. And we took a sample size of 30. So this gives us a value of 1,260 divided by 954.86299919. Once again, you realize I did not round anything, and I will just do the calculation and round once at the end to 2 decimal places. So this gives us a value of 1.32 when you round to 2 decimal places. So the question is, where does that fall on our graph? Well, it looks something like this. I'll change colors here. And if we were to plot 1.32 on our graph, you see that it's here somewhere. Okay, we don't have to take our rulers out to measure this exactly, but we know that it's less than 1.65. So this is our test value. Okay, so the test is 1.32. All right, and falls in the non-critical region, or the region where we do not reject. So by making our decision, right, what is the decision that we make? Because that's the 4th step, is to make the decision. And the decision in this case is do not reject. So do not reject. Now, what is it that we do not reject? We do not reject our null hypothesis. Okay, so let's go take a look at our statement. We are not going to reject the statement. Okay, so we are going to accept that the mean is actually less than or equal to $42,000 is really what we're saying. Now, you might ask yourself, wait a sec, we did a sample, and our sample had a mean that was greater than 42,000. What do you mean it's not, the population mean is not less than 42,000, or isn't greater than 42,000 like we're trying to prove here? Well, when you factor in the standard deviation and the sample size, that changes the picture. We're not far enough away from 42,000, which is right here. We're not far enough away in terms of standard deviation and size of the sample to actually state that we're further or larger than $42,000. Okay, so the standard deviation and sample size play a huge role in determining our outcome. So we do not reject H naught. And then last, what we're going to do is we're going to state our findings. And we're going to make our statement based on our alternative. Okay, so we look at our alternative, and it says that the mean is greater than 42,000. So we're going to state the following. Our sample data does not indicate the population mean income of IT graduates is greater than $42,000 per year. So you notice that I stated my conclusion based on my alternative hypothesis. Now, with that said, let's just recap what the steps were. Step 1 was to state the hypotheses. Step 2 was to find the critical region and values. Regions values, right? So we found our fence, so to speak. Step 3 is to perform the test. Z-test or t-test if it's a small sample size. Step 4 was to make a decision. And then last, state our findings. So the process is always going to be the same. Okay, just those 5 steps. What's going to change is the different scenarios. Is it one tail or two tail? And to what level of confidence we are interested in performing our test. And so just as long as we do these 5 steps, we should be fine. Now, just make sure that your hypotheses are properly stated, because if they're incorrect, then everything else is going to be wrong, right? So let's make sure that we really understand what the question's asking, because everything else is really pretty straightforward. I'm going to do the next example on the next video.